-1. Oh yeah, we're going. We're recording. All right, hi. Welcome back to Math 234. I'm your host, Steve Dragoo. Today, we're mixing two section sixes. So the tying thread is section 6 in two ways. But half of it's chapter 15.6, the other is chapter 16, section 6. So we've already kind of covered half of the chapter 16, section 6, like half a semester ago. That's when we did parametric surfaces. So just as a quick reminder there, we've done two types of parameterizations. We've done parameterization of curves, which is reducing a 3D object down to one dimension, right? A curve being a line, so it only has the one parameter, one dimension. And then we also got parametric surfaces, which is taking a three-dimensional surface and reducing that down to two dimensions, so two parameters. Right? In each case, when we're doing a parameterization, we are taking some higher dimensional object and reducing it down to fewer dimensions. So two or three dimensions down to one in the case of a curve, or three dimensions down to two dimensions in the case of a surface. Meaning we'll start with x, y, and z, but replace those variables with parameters, usually s and t. Right, so that is the bit of section 16.6 that we've already done. Again, parametric surfaces. And both of these other two sections will do, hey, cut that out. Both of these other two sections do surface area. So there's a version of it from chapter 15 where we just look at surface area of explicit surfaces. So those are the kinds where z is a function of x and y. So if z is already a function, there's no need for parameterization because we already can express the entire shape with just two variables or just two parameters, that being x and y. So when we get to parametric surfaces and parametric surface area, so that's our connective tissue, we'll need to replace x and y and z so that we still have functions. So we do parametric surfaces when z or x or y can't be expressed as a function of the other two variables. So when we need to have a function somewhere, parameterization is what will get us there. But that means we've got like two slightly different formulas that will ultimately end up sort of meaning the same thing. Both of them are for surface area, and here's the first one. Again, this is for explicit surfaces. So z being a function of x and y, so I can have my double integral, which will get me surface area, just using x and y. No need to go to our parameterizations just yet. So again, if that function is z equals whatever all my other stuff is, I can just take partial derivatives with respect to x and y, and then plug them into this surface area formula, which looks like what you see on screen, the partial x squared plus f partial y squared plus 1 squared, and then the square root of all of that. We take a double integral of it. So a decent way to think about this formula is really just partial x squared plus partial y squared plus partial z squared. But if z is a function of x and y, then partial z is going to be 1, right? Derivative of z with respect to itself should be 1. This is why that third term is 1 instead of partial x or partial y. If we harken back to some Calc 2 ideas, and when we did arc length even earlier in this class, we had this formula for arc length, which is just f prime squared plus 1 also squared, where again, that 1 is coming from the derivative of y with respect to itself. Kind of. I at least like to think about it that way because it helps me remember what I'm doing. But anyway, arc length, just if we extend it to its higher dimensional idea, that's going to be surface area. So, we might look at, again, an explicit surface. In this case, I've got z equals x squared plus 2y. I can get its two partial derivatives, that being 2x and 2, and plug those into a surface area formula. these integrals tend to be a little more on the nasty side since we've got to integrate something that's on the inside of a square root. So, a little unfortunate that, but we'll make it work. Oftentimes that means we'll just plug our numbers in after an integration and then not worry too much about simplifying it down. Because this does simplify some, this expression, this 1/8 times 2/3 times blah, 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 blah. It'll simplify a bit, but not enough to really make it worth it. So I'll oftentimes leave an answer right here so you can hopefully see where each piece is coming from. But also, I think revisiting parameterizations is not a bad spot to start with this section. Again, we'll need to do some parameterizations of surfaces in this unit and all the rest of the units going forward. So let's just go back to that real quick. In a parametric surface, we want to replace x, y, and z with our two new parameters, usually s and t, though the textbook likes to use u and v, but we'll come back to that if we need to. In the case of this example right here, I'm able to still solve z is a function of x and y for the surface that I have, because that thing is a plane. Notice it's x plus y plus z equals 2. So if I just solve that plane for z equals something, in particular, I think it's 2 minus x minus y is what z is equal to, then I can just replace x and y with s and t and get my parametric surface. When it's a parameterization, it'll take the form of a vector equation. So I've got this r of s and t, which again ought to look a lot like that r of x and y that's just right above it. Again, with an explicit surface, I can just keep using x and y as my two parameters. But I kind of wanted this as a connective tissue to tie at least some of the ideas between x and y into the parametric variables s and t that we'll use. So our sort of dream, or one of our hopes and dreams when it comes to parameterizing a surface, is that I can just replace two of my variables with s and t and just hope that something nice shakes out. It'll be the case some of the time. But in other cases, it won't be that nice. But we have a lot of standard types of parameterizations that we go to. Polar coordinates is a very handy parameterization if we're trying to do something that's circular in nature, as well as cylindrical and spherical coordinates, if either of those systems seems to fit our shape better. But again, we'll start thinking about those if we have circular regions. But before we dive too far into that, quick overview of what this surface area looks like and where it comes from. Basically, we're going to divide up our surface into a whole bunch of grids. It's some curved surface through 3 space, so it tends to look a little weird, right? We're not going to have nice straight lines everywhere. They'll all be curved. But if we instead try to approximate those curved lines with straight lines, we can come up with a fancy integral formula. So basically, we'll parameterize our surface, split it all up into that grid shape so that each has side lengths of delta s and delta t. And then we'll approximate all of that stuff with the vectors delta s times r partial s and delta t times r partial t. Again, r is our parameterization, meaning that the sum of all of those areas of parallelograms together should give us a really good approximation for that surface area. Again, it'll be an approximation. You probably might recognize that since we started introducing the notation that usually goes into a Riemann sum. And the real handy trick is noticing right here in the work of getting down to the bottom, here near the end, that, oh, wait a minute, skipped a step. Before I get there, we should first remind ourselves that all the way back in chapter 12, like the second week of class, We figured out how to calculate the area of a parallelogram. It's the magnitude of a cross product. Should say that part first. So that's kind of what the whole next part really hinges on. Right? If we take the cross product, first of all, that gives us a vector that is orthogonal to both of the two vectors I used to create the cross product. But also, if I take the magnitude of that cross product, I get the area of the parallelogram that's formed by the two vectors I started with. So if I want to calculate the area of a bunch of parallelograms, I should take some cross products. Specifically, I want the cross product of the two vectors I would use to make that parallelogram. Right? And so we're going to get a magnitude of that. Then the handy trick that I jumped ahead on a little bit is noticing that delta S and delta T are just constants, meaning I can pull them out of that magnitude. Because they are going to be just constant values, just the total length of the thing divided by the number of rectangles I want to use, or the number of parallelograms I want to use. So you can pull this out of the cross product and then do the usual Riemann sum type stuff, where we turn that sum into an integral. Delta S and delta T become ds and dt. So ultimately, we're looking at integrating the magnitude of a cross product. And to connect the two ideas together, magnitude of a cross product is usually the square root of three square terms added together, which is almost exactly what we saw in the 15.6 formula. Square root of three things added together. Squeeze three square things added together. Jeez, I'll get there eventually. But cool. So that's our formula. And from there, we are just going to use it as often as we can. So the parametric surface area process is often a gigantic pain. So the first example we're going to do is sort of already done for us. But just to emphasize the fact that, again, this formula can be a gigantic pain if I've got to parameterize this whatever thing that it might be. I know I'm going inside of the cylinder that is given by x squared plus y squared equals 4. So I'm going to look for some kind of a decent parameterization. Maybe I try to go to polar coordinates. So I'll use s cosine t and s sine t as the replacements for x and y, since that's often a decent looking parameterization, especially when my region is circular, which we have here, x squared plus y squared is equal to 4. So my parameterization is going to be, again, s cosine t and s sine t for x and y. I'm looking at this bit right here. Come back here. Which, again, basically just polar coordinates, r cosine theta and r sine theta, but I'm using letters s and t instead of r and theta. So s for r, t for theta. And then, once I've got x and y, I'll just try to replace them in my equation for z, which is this guy right over here. And hopefully something that I can solve will show up. I can solve that equation for z, which gives me the replacement part over here. 5 plus s sine t minus s cosine t over 3, which is basically 5 plus y minus x over 3. Right, but I'm looking to parameterize the surface that I'm hoping to find the area of. So it's got to be the tilted plane that I'm parameterizing. It's always the thing that I want the area of that needs the parameterization. There's usually going to be two equations or two surfaces that you might see within a problem. One of which is going to be the thing I want the surface area of. The other is just a restriction on the domain. So I don't really want to parameterize x squared plus y squared equals 4. I want to use that to help solve the problem after my parameterization. But again, I go to the thing I actually want the surface area of to get that parameterization. But then once I have that thing, I know I need the cross product of two partial derivative vectors. So I will take those partial derivative vectors, calculate a cross product, which I don't think you really want to spend a bunch of time trying to write all of this down because it's a lot. So maybe skip that part. Just know that a whole bunch of simplification is going to go on. Almost every single simplification that happens in this process is using the trigonometric identity. Sine squared plus cosine squared is equal to 1. So that Pythagorean identity shows up a heck of a lot in this simplification. But ultimately, it comes down to something that isn't too terrible. S over 3 times the square root of 11. And then that's the thing that we're able to integrate. It took a whole bunch of work just to simplify that cross product. And then we can go through and actually calculate what our surface area should be. And the handy hint shown off here at the end, we know that this thing that we just calculated, we're sort of projecting a tilted plane down into the xy axis where we see we've got a circle with a radius of 2. So if we take that circle with a radius of 2 that's on the xy plane, and project it back up to the plane where it should be, it's going to become a tilted circle. It's basically a circle that gets stretched out along the diagonal. If that argument hopefully makes some sense. Since that circle is being tilted and stretched, I would expect its area to be larger than the area of the circle that it started from. So I think that the area of the projection of the circle back into the tilted plane should be more than 4 pi. Since that would be the area of the circle just in the flat xy plane. This thing, again, has been stretched, so I expect its area to be a little bit bigger. And that's what we ended up finding in that problem, or, well, the typed up version of that problem. 4 pi, well, if we maybe rewrite that to look a little friendlier, this is 4 pi times the square root of 11 over 3. And square root 11 is more than the square root of 9. So that coefficient at root 11 over 3 is going to be bigger than 1. So a value larger than 4 pi is my argument there. Cool. So, oh, hey, yeah, since root 11 is bigger than 3, it's right there. The thing I want you to take away from that problem is that it's a mess and a pain. And ideally, we don't have to do that every single time. That's why we're tying these two sections together. Because unless we're explicitly told that we must parameterize some object in order to calculate its surface area, we could just rely on the 15.6 method to get a surface area instead of doing that cross product of two partial derivative vectors. As long as we have an explicit surface, which a plane is going to be an explicit surface. We know it's 5 minus x plus y over 3, or z equals that. So we can use that as our function, f. Right? It's 5 minus x plus y over 3. So then f partial x is negative 1/3, and f partial y is positive 1/3. And I can just go to that surface area formula that we had right at the very beginning, which says I want the square root of partial x squared plus partial y squared plus 1 squared, dA. And then just plug a few things in. So this will be the square root of negative 1/3 squared plus positive 1/3 squared plus 1 squared, dA. And a bunch of that is going to simplify out rather nicely. Notice that there are no variables left on the inside of that derivative. In fact, on the inside of that square root, everything is just a number. I've got 1/9 plus 1/9 plus 1, or 9 over 9. The inside of that should just work out to the square root of 11 over 3. But since adding all of that up, I'd have the square root of 11 over 9. The denominator is a square number, so I can simplify that part. So I end up with just square root 11 over 3 times the double integral of dA. And if all I'm integrating is dA, I get just the area of my region. So I think this is root 11 over 3 times the area, which is root 11 over 3 times, just look back at our problem. What area are we actually integrating over? Well, that's inside our cylinder. So this is our area right over here. Or the thing that's going to tell us our area. I think that's a circle with a radius of 2. So that'll be times 4 pi. Pi times 2 squared. We'll write it in its pi r squared form. Right. Emphasize where everything is coming from. So I can use a trick or two to avoid integrating where possible. And so that'll work for at least a couple of these examples, but I know there's a nasty one coming up where we won't get to do that. So between the first two problems we just talked about, one of which is a relatively straightforward method using the nice explicit formula for surface area, and the other one, again, is a gigantic pain. So where possible, we'll want to use the nicer formula for surface area. If we can make that work, it'd be a lot nicer to use that than needing to do all of this every time. So let's see how many more times we can use the nice formula before we run out of gas. Okay, let's see. We are looking for the area of the part of the cylinder y squared plus e squared equals 9 that is above the rectangle with the vertices shown right there. So the cylinder y squared plus e squared equals 9 is not an explicit function. Right, so we've got a cylinder that is sort of laying on its side, and it's expanding along the x-axis, since that's the variable that I don't see. Right, think I've got circles with a radius of 3 in the xz or in the yz plane. Maybe let's go draw that shape real quick. With like, I don't know, this into this. Make you slightly bigger. Cool. Something like that. And then that surface is kind of doing one of these as it expands along the axis that we want it to. Ooh, hey, don't give me that. Redo. Paste that shape again. And one more time, just to try and make this thing look as nice as possible. I think our cylinder kind of looks like that shape-ish, right? Expanding along the x-axis. So technically not an explicit surface, because it wouldn't be a function if I try to solve for z. But since we're only asking for the part that is above that rectangle, and notice that that rectangle is smaller than the radius, so it's entirely inside of that cylinder, we can have an explicit function for just the top half of that cylinder. So if I solve that thing for z, I can call it just the positive square root of 9 minus y squared. Maybe that one's not so bad. Oh yeah, that is this one. And that will let me start calculating some partial derivatives. So actually, I know I'm going to need a lot of space over there. So how about I move this down to here? Z is the square root of 9 minus y squared. So f partial x is 0, since there is no x variable in there. That part's kind of nice. F partial y is a little bit less nice. Let's see. This is going to be 1/2 times 9 minus y squared to the negative 1/2 times negative 2y. And we'll probably want to simplify that a little bit. So let's see, the 2's can reduce. So this looks like it's just negative y divided by the square root of 9 minus y squared. Try that again, maybe zoom in. Square root 9 minus y squared. There we go. Now to get a surface area, we need to go plug some stuff in. So this is the square root of 0 squared plus, this will end up being y squared divided by 9 minus y squared. So I'll square that partial y element. And then I've still got to add 1. So that's what our formula tells us to do. Slap a d over here and a dA there. And start trying to calculate that thing. So this is going to be something after I slide you over to the right. I am after the double integral of this inside mess, which I'm going to try to simplify. Put the top in my square root later. I've got y squared over 9 minus y squared plus, if I look at that 1 plus 1 part, change it to a fraction so that it adds up with the other piece. This is 9 minus y squared over 9 minus y squared. Now put that hat on. Worry about what dA is in a minute. This expression actually simplifies a little bit. Right, now that I've got my common denominators here, y squared plus 9 minus y squared, I'm just going to be left with 9 up top. So this looks like 3 times the double integral of 1 over the square root of 9 minus y squared. And then let's just go ahead and throw dx and dy on here. How about dy then dx? X, I think I saw, went from 0 to 4, while y goes from 0 to 2. And then we have to integrate that. Integrating 1 over the square root of 9 minus y squared. And I'm pretty sure that's trig substitution. So let's go give that a shot. So I need a right triangle. We are after the square or the integral of 1 over the square root of 9 minus y squared dy. So if I'm taking the square root of 9 minus y squared, I want that to be a square number minus another square number. So 3 being the square root of 9 should be my hypotenuse, and y is going to be one of my legs. That way, if I apply the Pythagorean theorem to this triangle as it stands, that thing is the square root of 9 minus y squared. I'm going to add in a theta right there because I'm going to call that thing an angle. Brilliant. Looks like a decent start. I'm going to use that triangle to replace my y variable. Keep a hat going right there. What do I want to say about this stuff? I think I want to say y is equal to 3 sine theta. Again, recall from trigonometry. Sine is opposite over hypotenuse. So y over 3 is sine, meaning if I solve that thing for y, it's equal to 3 sine theta. 3 times sine theta. 3 times opposite over hypotenuse. Blah, 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 blah. Then I can take a derivative of that to figure out that dy is 3 cosine theta. Right? Still all positive. And then I can go over to my integral and start replacing stuff. So my denominator, the square root of 9 minus y squared is going to be 9 minus 9 sine squared of theta. Right? Since y is going to be 3 sine theta. dy is 3 sine theta d theta. Then I want to start simplifying that. Maybe it doesn't look too bad. So that's 1 over the square root of, and actually let's not call it 1 over just yet. Hey, cut that out. Whatever. 9 minus 9 sine squared is 9 cosine squared. Right, from our Pythagorean identity, we know we can replace that. Ooh, wait, hold on a second. Here's some whispering back there, and I think I know why. dy, right? I needed to replace that. And I definitely wrote down that dy is 3 cosine theta. But then I said it was 3 sine theta. That was just an error. This should say 3 cosine theta. D theta right there. There we go. Seem fair? Yeah. All right. Brilliant. Then I'm just going to move that 3 cosine theta into the numerator. D theta, I'll just leave over there for now. And then this thing is the integral of 3 cosine theta divided by the square roots of 9 cosine squared theta, which is also 3 cosine theta d theta. And hey, look, it all cancels as long as cosine theta is greater than 1, or greater than 0, which we'll just gloss over that part for a bit. This is just the integral of d theta, which is theta. All that just to integrate one piece. So come back up to our definition for y, which was y equals 3 sine theta, which means sine of theta is equal to y over 3. So theta is the arcsine of y thirds. y over 3. So this thing integrates to arcsine of y over 3. Wasn't that so much fun? So let's go use that to solve the rest of the problem. So back to right here. Maybe move you up a little bit. make you a bit smaller so that I have space to write an answer down. This thing is equal to 3 times 4 from the dx integral times that y integral evaluated between 0 and 2. We just did all that work to say it's the arc sine of y over 3. So this will be arc sine, or sine inverse of 2/3 minus the arc sine of 0. And if I take the sine inverse of 0, or effectively asking, what angle gives me a sine value of 0? That's conveniently 0 radians. So arc sine of 0 is 0, as opposed to arc cosine of 0, which is 1. Or arc cosine of 1, which is 0. Said that backwards. But anyway, we get this thing. That simplifies a bit. 12 sine inverse of 2/3. But yeah, every once in a while, we'll need to do some nasty integral. And maybe you could remember all of that just from like an integral table. You happen to remember what arc sine's derivative is. You might have been able to just integrate that thing right away, just using a formula, but I never remember those. So I just draw a triangle every time. Different schools of thought, I suppose. It's not the worst integral in the world. I'm sure we've done worse. That said, wouldn't expect an arc sine integral to show up on an exam. That's a little more than what we're after. These problems are hard enough as they are. All right, let's try another one. Express the area of the surface. Hey, look, we've got another explicit surface. Isn't that grand? That lies above the disk. X squared plus y squared is less than 4 in terms of a single integral, but then do not evaluate it. Because as it turns out, it's going to be nasty. So let's get a couple of partial derivatives over here. Partial x. It's going to be negative 2x e to the negative x squared minus y squared. Partial y, negative 2y e to the negative x squared minus y squared. Take my two derivatives, which is all I need to plug into that formula. So this will be the square root of 4x squared e to the negative 2 x squared plus y squared plus 4y squared e to the negative 2 x squared plus y squared plus 1 dA, and then we'll put a D down there to indicate we're going over the region D. Right, if I square those two partial derivatives, I think I end up with this expression right there. Now, two things are telling me pretty strongly I should start considering polar coordinates. Right? I'm looking at a region that is inside of a disk that is just a circular disk. X squared plus y squared is less than or equal to 4. Sounds like polar coordinates. Also, I'm seeing a lot of x squareds plus y squareds show up. So I'm thinking polar coordinates might make a lot of sense. But if we take one more step to simplify this thing, I've got 4 times x squared plus y squared e to the negative 2 times x squared plus y squared plus 1 still over dA and the disk. And now I think there are a few nice substitutions I can make inside of that integral. So this looks like the square root of 4r squared times e to the negative 2r squared plus 1 times dA, which don't forget dA is going to be r dr d theta. Theta from 0 to 2 pi and r from 0 to 2. We're going all the way around the circle. The circle has a radius of 2. And I think that that is set up. Right. It did say do not evaluate. So why don't we leave it right here? Suppose there's one more step we could take since there's no theta dependency. We can just do the integral from 0 to 2 pi d theta and just get 2 pi. So then it's 2 pi times a single integral. But I think you'd agree that that integral does not look like a lot of fun. So we're not going to solve that one. But one final example. We haven't for reals done a parametric surface area problem yet. So one example where we do that. Again, we're just going to set it up and not evaluate it. Because the setup is the fun part. Fun in a lot of air quotes. But what is it we're after over here? So we're given a surface. We've got a parameterization just given to us. R of st is going to be st squared, with s between 0 and 1 and t between 0 and s. So using that parameterization, set up a double integral that will express the surface area. So we need a couple of pieces. We need r partial s, which is 1, 0, t squared. Right, if I just take partial derivatives with respect to s down that line. I also need r partial t, which is 0, 1, 2 st. Right, I'm looking right here to calculate those guys. Whatever my parameterization is, go take some partial derivatives of it. The spot. And now I'd really like to get the cross product of those two vectors. So I want r partial s cross r partial t, and it'll look something like this. I, j, k goes across the top row. 1, 0, t squared across the middle row, and 0, 1, 2 st across the bottom row. And turn that thing into a cross product. What do we get? All right, first, 0 times 2 st is 0 minus 1 times t squared. T squared. Then t squared times 0 minus 1 times 2 st. And finally, 1 times 1 minus 0 times 0 is 1 minus 0. That looks like my cross product right there. Isn't that so fun? Then what we really wanted was a magnitude of that thing. So suppose let's get ourselves a magnitude written down. I don't want that to be a vector. I just want it to be a line. There we go. So the magnitude of that vector is just the square roots of the 3 components squared. So t squared squared is t to the fourth power. Negative 2st squared is 4s squared t squared. And 1 squared is 1. Adding each of those up, I've got myself a magnitude. So finally, I can express that surface area as the double integral of the square root of t to the fourth plus 4s squared t squared plus 1. I think we've got to do dt first and then ds. If we roll back up to our parameterization, yeah, we're told t is bounded between 0 and s. So dt between 0 and s. And then ds was between 0 and 1. And again, I just wanted to set it up, not actually calculate the thing, because again, that integral looks kind of nasty. So let's just not do it. Setting it up, it's fine enough. All right, yeah, I think that takes us to the end. If it's been a while since you've seen parameterization and you're still kind of stuck on that stuff, there are 2 bonus videos from Khan Academy that I think do a decent job of explaining parameterization. So I've rewritten the links so that they're hyperlinks in my notes, so that you can just click on them there if you want to go look at it. I suppose the last thing was this thing also could have been done explicitly, and it was a lot easier once again. But we get the same result. Anyway, that's it for me. I will see you guys again on Friday, where we do surface integrals. Oh boy. Okay, bye. Bye, bye, bye. Bye, 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 bye.